Now, dear students, chapter number 5 and laws of motion. And today we have to be discuss the following topics. And earlier we have already discussed the motion of a car on a level curved road. Further, I'll just taking this one topic along with the new concept, that is motion of a car on a banked road, and along with the need of banking, and one of the topic we will cover along this topic, that is bending of a cyclist, that from the vertical how much it lean the cycle so it can easily make the turn on a curved road. So earlier we have already discussed the motion of a car on a level curved road. Further, I am just discussing this one topic. So the whole topic will be as a group will be will in front of you. So I am just assuming that there is a movement of a vehicle on a level curved road, and initially the vehicle is moving on a straight road. Okay, it having its own velocity. So whenever it making the turn on a curved path, so it should sustain its velocity. So easily it will be available on this path on this curved road. Okay, so how it is possible? So here there is a need of the force of friction which develop the necessary centripetal force, and this centripetal force will keep the body on a circular path. And already we have discussed the concept of the centripetal force. So what is the role of the centripetal force? We have centripetal force keep an object on a circular path. Okay, so as per the nature, we have already discussed the coefficient of the friction. So there is a standard value of the coefficient of friction which provide the necessary centripetal force on this road. And if we want to increase or we want to sustain our velocity, so we have to be keep the velocity in this manner. So we got the force of friction which should not be greater compared to the friction that is available on the road. If it is less compared to the that mean force of friction that is available on the road, so there is a no problem. If we are just increasing the velocity, so there is a certain problem that we need the greater force of friction. Okay, so if the surface having the less force of friction, okay, and we need the greater force of friction, so we can skid from this surface. Okay, so we are just assuming that force of static friction should be greater compared to the centripetal force. Okay, and we know that necessary force of friction will keep the vehicle that mean vehicle on a surface. So we are just writing here the basic that mean nominations of the formulas. And here we are just using the basic FBD, and the weight of the car is acting is vertically downward, and in the reference we are just getting the normal reaction in a upward direction. Okay, and the consideration of the centripetal force will be along the radius towards the center. Okay, so we are just following this one situation, and we know that Fs is equal to Fs is equal to mu Sn. This is the one of the basic formula, and n is equal to mg. So we are just keeping this one in mind, and we are just using mu s is equal to mg. So this is the equation number 2 we have, and somehow we have the formula of the centripetal force, that is called the mv square upon r. So this is the equation number 3 we have. We are using the equation number 2 and 3 in the equation number 1. So what actually we are getting? Mu s mg greater than and equal to, that is mv square upon r. So m to m is cancelled. If we are just writing that v square should be less than compared to the mu s rg. Okay, so mathematically I can write that v less than under root of mu s rg. Okay, so this one we have already done. Now I am just writing that in the part of the equal, that mu s r g. Okay, so this is the one of the that mean basic formula I have, and this is the permissible velocity of the safe velocity we have, which is required on a curved road. And v safe velocity is very much depending upon the coefficient of friction that is available on the road and road. Okay, and generally coefficient of friction upon depends upon the nature of the surface we have, and the v safe velocity we have, or the permissible velocity, is directly proportional to the radius. And somehow if we want to increase, or we are just keeping the very high velocity, so there is a need to be increase also the radius also. If you are just increasing the velocity and the radius will be less, so we will skid from this surface. Okay, so these are the two parameter, and we have need the safe velocity. Okay, now we are discussing the motion of a car on a banked road. First that banked road. Now, students, motion of a car on a banked road. So, first I am just giving the little bit brief of the banked road. So, it's simply a process to raise the outer edge of the road compared to the inner edge by the small angle of inclination. Okay, it's simply the process to raise the outer edge of a curved road. We are just doing generally on a curved road. So it's a simple brief we have about the banked road. So we are just increasing the outer edge of the road compared to the inner edge by the slight small angle of inclination. Okay, this phenomena generally is called the banking of road, and this angle through which we have raised the outer edge is called the angle of banking. So this is the simplest meaning we have. And first we want to discuss that what is the need of the banking of a road we have, and how can we utilize this one concept to make the sustained movement on the curved road. Okay, so as we have done the movement on a motion, we have done the motion of a car on level curved road, and we have discussed the basic formula, that is uh, mv square upon r, that is called the mu s mg. Okay, so here we are just assuming that mu s is fixed for the surface, even the r is also fixed we have for the surface. Okay, surface, that means radius of the circular turn, it is also the fix. If we want to increase the velocity, so probably we have need the friction. Okay, so we are just making the concept of the velocity on a curved on a level curved road. Suppose we have the velocity, and the surface which having the standard force of friction, that is 100 Newton, and that is a safer, that mean which develop the necessary centripetal force for the particular velocity. Suppose we have the velocity through which we are moving, that is called the 10 meter per second. So it required the force of friction to easily make the turn on the road, that is called the suppose 50 Newton, and we know the capacity of the friction that provide the necessary centripetal force, that is called the 100 Newton. Okay, now slightly we are just increasing the velocity 20 meter per second, and slightly there is a need of the that mean friction on the road which is required to be sustainable, that mean moment, that is 60 Newton, and still it is a very much less compared to the actual value, which is the maximum value, that is called the 100 Newton. Suppose we are just increasing the velocity 40 meter per second, and somehow we have need, that mean we have required the 1110 Newton, 1110 Newton of the that mean force of friction, and it is very much greater compared to the actual value. So what will happen in this case? We can skid from the road. Okay, suppose we are just increasing the velocity 60 meter per second. So further we have need to be sustained that on the surface, that is called the 120 Newton. So in the both the case we can skid from the road. So to develop the necessary force of friction, what should we do? So that's why we are using the basic concept of the banking of road. Okay, so I am starting. I hope you can easily understand that what is the need of the banking we have, and through the banking of road we are just making the necessary centripetal force by the help of a component of a normal reaction along the horizontal direction that provides the necessary centripetal force to us. So that's why we are just using the concept of the banking of road. Okay, so one of the basic define I have written here: the process of raising the outer edge of a curved road above inner edge is called the banking of road, and the angle through which the outer edge is increased is called the angle of banking. So here further I can drawing the basic diagram. So this is the curved portion of a curved road we have. Okay, as we are just increasing or tilting the outer edge by a small angle. It is not, this angle is not the too much large. So this process of that increasing the outer edge compared to the inner edge by a small angle of inclination is called the banking of a curved road. Now, dear students, I am just imagining in a car, that means on a banked road. Here I just made the angle of elevation, which is very small, as I am just keeping the car on a banked road. Okay, that is moving, and here we have the that mean object, and the weight which acting vertically downward, and the car vehicles sorry and the tires of a car is making the normal reaction to the surface. Okay, so that mean car tires of a car applying the force on a surface, so it surface offers the normal reaction to it. So here just I am making that how we are just assuming the component of the normal reaction. So I am just imagining this one is a surface we have, this one is the surface we have. Here we have the x-axis, here we have the y-axis. Okay, now as we know that the weight is acting vertically downward, and the normal reaction there just that mean above the surface we have. Okay, and it is be represented by the n we have. Now we are just assuming that we are just completing this one portion, and suppose this one is the that mean elevation angle, that is called the theta we have, and this one is the 90. So what is the value of this angle we have, that is called the 90 minus theta we have. If I am just making the complete angle, so this is called the 90. If this is 90 minus theta, so this one angle will also the theta. If this one is the theta, so just vertically opposite angle, that is called also the theta. So we can easily make the component of the n in a y direction, that is called the n cos of theta. So easily I am just putting this one component, that is n and cos of theta. Here in the along the horizontal direction and towards the center O, this is the suppose center O, and the path having the radius r. So in this direction we have the component that is called the n sine theta. Okay, so this is the resolution of the component of the normal reaction. Somehow we are just assuming the force of friction. So here just I am representing, this one is the force of friction we have. Okay, so this one is the theta, so this one is also the just opposite angle we have, that is theta. And suppose this is the part of the friction we have, so here we have the basic component that is called the fr cos theta. Okay, and in the vertical downward direction along the mg we have the component that is called the fr sine of theta. Okay, so we have the made the basic resolution, and that component we can also trace here easily. So this is the portion of the fr we have, and along this direction we have the component that is called the fr cos of theta. Same component that I am plotting as in this diagram. I have sidewise made all the things. Okay, so easily you can understand the meaning. And in vertical downward direction along the mg we have that fr sine of theta. Okay, now we have applied the basic FBD, that mean concept, and now we are just making the conclusion of the net upward force, net downward force, and the component of the forces, those are just responsible for the force, centripetal force. So I just want to say here that we want the force, centripetal force, by the help of a component of a normal reaction which act along the horizontal direction, and this component along with the friction will make the help to be stay on a that curved road. Okay, so in this case we are not totally depending upon the friction. We have developed the additional reaction of the normal component, okay, which also helps to develop the necessary centripetal force. So we are eligible to develop the centripetal force which responsible to stay the vehicle on the road without the help of a too much friction between the tires and the road. So one of the another benefit we have, without any kind of the wear and tear of the tires, we can safe negotiate on the curved road. Okay, as we are just using the concept of the banking. So in this process there is a need of the banking we have to reduce the wear and tear. So banking also reduce the wear and tear of the tire, because we are not totally depending upon the concept of friction. We are developing the centripetal force by the help of a normal component of a normal reaction, okay, which act along the horizontal direction. Okay, so easily we can make the movement of a on the curved road as we are just approaching the banking. Now we have to be discuss the what is the permissible velocity we have on the banked road. Now first I am just approaching the net upward forces are equal to the net downward forces. So in the upward direction we have the component that is called the n cos theta, and in the downward direction we have the two component that is called fr sin theta and the mg. So I have written n cos theta is equal to the fr sin theta and mg, and now I am just separating the meaning of the mg from this equation. Now the simple calculation I have done, that mg is equal to n cos theta minus fr sin theta. Now I am just making the conclusion of the net horizontal forces. Those are equal to the centripetal force. So in this manner we have the total horizontal forces are, first is the n sin theta and next is the fr cos theta, and these two forces develop the necessary centripetal force we have. So we are writing that net horizontal forces is equal to the Fc. Okay, so here we can easily pick up them, that n sin theta plus fr cos of theta, and the meaning of the mv square upon r we have. So this is the one of the basic equation number 2, and now we are just making the conclusion of that 2:1. So how we are just approaching it? Now equation number 1 and 2, and we are just approaching the 2:1. So I am just writing mv square upon r into 1 upon mg, that is equal to the n sin theta minus fr cos theta. Okay, so this one was n sin theta plus this one is a plus sign we have. Okay, this one we have also the plus sign, and then after we have the basic, that n cos theta minus fr sin theta. Now I am just cancelling m to m. So what is the max velocity we have? That is called the v square, and the rg we have, and we are just solving this one portion. Okay, now I am making the n cos theta from the each portion. Okay, so in the numerator I am just taking the n cos theta common. Okay, so here we have the n sin theta is to be divided by n of cos of theta. Okay, plus fr upon fr cos theta is to be divided by n of cos of theta. So this one was of that mean numerator we have. Okay, and denominator we have, I am also taking the common, that is called the n cos theta, and here we have that fr sin theta is to be divided by n of cos of theta. Okay, so we are just making the general cancellation, cos theta to cos theta, n to n we have. Okay, here in the bracket we have n to n cancel, and somehow we have cos theta to cos theta cancel, and here we have the general term. So little bit formula is coming in the particular shape, that is v max square rg, that is called the, here we have the, that means sin theta upon cos theta, that is called the tan theta we have, and plus fr upon r, fr upon n, that is the coefficient of friction we have. So I am just writing that is mu s. Okay, so this one is a that basic part we have, and closing of the bracket with 1 minus further fr upon s, that is the concept of the mu s and the tan of theta. So this is the one of the basic general formula we have got, and further I am just making the simplification of this formula. V max that square is equal to rg, and the bracket of that tan theta plus mu s is to be divided by 1 minus mu s tan theta. So this is the safest velocity we have, or the permissible velocity at the concept when we have made the banking by an angle, small angle rg, that is called the tan theta plus mu s is to be divided by 1 minus mu s tan of theta. Okay, so this is the permissible velocity we have. What actually the V max we have here. This is the equation number 3 we have. What actually the V max here we have. V max is equal to maximum permissible velocity on the banked curved road whenever we have the availability of the friction. Okay, so we will not skid from this path. Suppose the one of the important case we have in this section. Now what is the special case we have? If surface is very smooth and the no friction is there, so we are just assuming that mu s is equal to 0. So the max velocity will be the optimum velocity we have, and it's having its value, that is we are just keeping the mu s is equal to 0 in the formula. So we are just getting mu v optimum is equal to under root rg tan theta. So still if the no friction is not there, so the angle which makes the helps to stay on a curved road. So this is the part of the, that mean angle of banking we have. So we have discussed the next formula, that is V max will be considered as a V optimum. Okay, so this is the special case we have. Now I'll just taking the what is the need of the banking we have. First, I am just saying that banking reduce the wear and tear of the tires. Okay, because we are just shifting our dependence on the force of friction. Okay, now second point we have. Now next, as we want to increase the velocity, so component of the normal reaction. So as we want to increase the velocity, so we have need the more force of centripetal force. We have need the more centripetal force. So here we have the one of the special component, that is normal component of the normal reaction along horizontal direction, and that component is called the n sine theta. It is very helpful component, that is called the n sine theta, which develop the additional centripetal force, and we can easily sustain on a sustain on a banked curved road. Okay, so this is the need of the banking we have. Now one of the basic query we have, that how much a cyclist lean the cycle from the vertical so easily it can make the safe turn on the curved path. Okay, so here just we are just assuming the case that this is the part of the surface we have, and this is the portion of the vertical that mean axis. Okay, and somehow as the turn is there, so the cyclist lean its cycle from the vertical. So I am just putting the tire of a cycle that it can make the turn, that cyclist can make the turn, so from the vertical. Okay, so this angle is the supposed theta we have, as he is leaning the cycle, so it can make the easily turn on a curved path. Okay, so here we are just resolving the factors. Somehow the tire pushes the road, so it gets the normal reaction. Okay, so this is the part of the normal reaction we have. Okay, now we are just assuming the concept of the weight, that is called the mg. Okay, here we know that the component which balance the mg, that is called the, suppose this one is a theta, so this is also the angle theta. So this one we have the n cos theta, and here we have the component of the normal reaction along the horizontal direction, that is called the n sin theta, which develops the necessary centripetal force. Okay, so we are just making the little bit dynamic, that means FBD here. So n cos theta balance the mg. So this is the first equation we have, and the n sine theta make the concept of the centripetal force, that is called the mv square upon r. Okay, so what is the permissible velocity through which it can make the negotiate and making an angle from the vertical? So we are just making the ratio of the 2:1. Okay, so I am just getting mv square upon r is to be at 1 upon mg, and the n sine theta we have, and in the part that is n cos theta we have. So n to n is cancelled, m to m is cancelled, so we are just getting that v square is equal to rg tan theta. Okay, and it makes the part v is equal to under root rg tan theta. So this is the part of the velocity, that is safer velocity of a cyclist, where he can make the leaning of the cycle from the vertical. So this is the one of the general formula we have, and so many numerical problem, those are available on this concept we have. Now, in the part of the summary, the basic formulas those we have used in this in derivative portion, that the safer velocity or the V max that on the level curved road we have. So we have discussed the formula that V max is equal to under root mu s rg, where mu s is equal to coefficient of friction of the for the surface we have, and it having its fixed value, that r is the radius and the g is the acceleration due to gravity. Now V max on the banked road. So Vmax is equal to under root Rg, and with the concern of tan theta plus mu s and 1 minus mu s tan theta we have. Okay. Third formula we have V optimum. As the mu s is equal to 0, we are just assuming the special case is there. So we are just getting that Rg tan of theta. Fourth number, Vmax when a cyclist leaning cycle from vertical. So we are just using the basic formula, that is V max, that is equal to under root Rg of tan theta. So this is the completion of this one topic, and you must do it by your own and see the video and prepare this one topic. It's an important topic of this chapter. Thank you.